All right, so section 1.3. Not a ton to really go through and teach here, kind of like the other sections. This is like very fundamental beginning of this particular chapter. And so we're going to take a look at a couple resources that you'll want to have to use, and then also just like what do some of these things mean. You just kind of have that voice tied to it. All right, so let's see. Why am I not changing screens? There we go. All right, so mathematical systems. Like algebra, the branch of mathematics called geometry is a mathematical system. The formal study of geometry begins with undefined terms we talked about in the past sections. Building this foundation, we can define additional terms. Once the terminology is sufficiently developed, certain properties or characteristics of the system become very apparent. These properties are known as axioms or postulates of the systems. More generally, such statements are called assumptions. So the key thing to think about this is that we have a series of axioms or postulates that we can just are kind of just already proven and already there that we can just accept and use. Once we have this vocabulary and accepted these certain postulates, many principles follow logically as we apply deductive reasoning. So thinking back to like deductive reasoning, it's the process of like, working your way through to make sure that we understand what's going on, to like being able to prove it. So these statements can be proved and are called theorems. And so theorems we'll be working to. So for right now, we just basically have like these axioms or postulates other people have proved that we can then use and apply to prove theorems. All right, so terms like point, line, plane are classified as undefined. We talked about in the previous sections. They do not fit any set or category that has been previously determined. So terms that are defined, however, should be described precisely. So like, for example, what does it mean to be a good definition? All right, so a good definition is like a mathematical equation written using words. A good definition must possess these four characteristics. So it names the term being defined. It places the term into a set or category. It distinguishes the defined term from other terms without providing unnecessary facts. And it's reversible. So a definition. So an isosceles triangle is a triangle that has two congruent sides. So in the definition, notice that the term is being defined, isosceles triangle is named. So you got number one, the term being defined is named. The term being defined is placed into a larger category. So a triangle. So it's placed into a set or a category. So it's an isosceles triangle. It is a triangle. A distinguishing quality that sets two sides of the triangle are congruent is included. So it distinguishes that defined term from other terms without providing unnecessary facts. So it's not an acute triangle, it's not an obtuse triangle, because it's an isosceles triangle because it has these two congruent sides. And it's reversible. So what does that mean? So if a triangle is isosceles, then it has two congruent sides. If a triangle has two congruent sides, then it's an isosceles. So those are the foundations of a definition. So reversibility of a definition is achieved using the phrase if and only if. So for example, we could define congruent angles by saying congruent angles are two angles are congruent if and only if these angles have equal measure. Vice versa, two angles have equal measure if and only if the two angles are congruent. And so that's this idea down here that we can look at this both ways. So it's if then, or we can take, so a lot of times what we think about this as, let me grab my pen. A lot of times what we think about this as is like, for example, this would be considered our P and this would be considered our Q. So then like, remember if we talked about conditional statements, this would be an if P, then Q, like this first one. Then vice versa, this would be our Q and this would be our P. So this would be an if Q, then P. And once again, that's the idea of if and only if. So now we can go both ways with that if and only if statement. So taking a look at more characteristics of a good definition. When we represent a Venn diagram, the definition above would relate to a set. So our set C would consist of all congruent angles to set E, which is angles with equal measure. So in this case right here, what we see is set E and set C are identical, or called equivalent sets. They're equivalent sets because of the fact that, sorry about that, they're equivalent sets because of the fact that congruent angles and angles of equal measure, that's by definition, they're exactly the same. So example 1, a line segment. A line segment is part of a line that consists of 2 points known as endpoints and all points between them. So state 4 characteristics of a good definition of a line segment. All right, so we got to start off with the term being used. So line segment is clearly being used. So a line segment, all right, we got it. A line segment is being defined as part of a line. So a line segment is part of a line. So there's our second part right there, part of a line. So what's it part of? And then the definition distinguishes the line segment as being specific to a line. So in this case right here, we say that the line segment is part of a line that consists of 2 points. It's known as endpoints and all points between. So that's stating the specific part of a line. And then the definition is reversible, and that's that if and only if. So that's that thing where here I have if P then Q, and Q would be this last part, or vice versa, Q, so if Q, then P. So we can flip those around to be able to get to that spot. All right, so I'm going to stop there with that one, and then we'll go to the second video will be about our initial postulates that we'll take a look at.